he actually has written a paper with Avrim and Adam.
Yep.
And you might hear about today, I guess. Right, so you tell us about venturing out into the world with AI.
Okay, great. Thanks very much. Yeah, thanks for inviting me to take part in this wonderful event with so many people I've known from different periods of time. Let's see. So I'm out in the Bay Area this year, visiting Google and Stanford, and I'm going to talk about some joint work that I've been doing with Prabhakar, which he alluded to at the end, and also it sort of logically in my own mind follows up on some earlier joint work that I did with Kian Vafa, Justin Chen, Sindel Mulanathan, and Ashesh Rambachan, which I'll start with for context. But I guess for context before all of that, first I want to join everyone in saying happy birthday to Avram. It's really wonderful to be a part of this event with speakers that include your family members and your former advisor and former students, and even people like me who just had the pleasure of getting to talk to you about ideas, write a paper together, have you generously host me at Carnegie Mellon 2004 to 2005. I've always really appreciated a few things about your work and you as a colleague. Obviously, I think everyone here, thinks of your work as just incredibly clean and elegant in the way you choose questions to work on. It's always very deep. And also somehow there's always a certain sort of joy in the work. I think like you take delight in the results. And you also take delight in other people's results. I feel like I've always learned things about my own work when I explain it to you, and you always say something that actually just makes me appreciate new things about questions even when I've thought about them for a very long time. It's of course funny that you can actually appreciate all these things about people's work even before you've ever met them. So when I was an undergrad, one of the first theory papers I encountered, not the very first, but one of the early ones, was this paper by 3 people that I had never met, although all of whom I've now had the pleasure of getting to work with. This one that Prabhakar began his talk with from Stock, 1991. And it had this very evocative picture of the room problem, the puzzle, as we heard. Now, what's funny is I actually now solve this puzzle on a regular basis because during my sabbatical I'm working at Google with Prabhakar and others, and I'm in this building called Gradient Canopy, which was actually built by architects who apparently were motivated by the room problem. And so the first time that 2 of my co-authors, Andrew Tompkins and Ravi Kumar, brought me to meet Prabhakar in his office, they said, we're going to have to leave an extra 10 minutes early to actually find it because it involves an online navigation algorithm. Now, I had the interesting experience of having an online navigation algorithm experience with Avram as well also. Avram and I were 2 of the 3 speakers along with Alan Borodin at a summer school on the island of Lipari. For those of you who know Lipari, it's a volcanic island north of Sicily. And we were 2 of the 3 speakers. We did some planning about the trip. It became increasingly concerning because in 2000 there was not a lot of information on the internet about how to get from Catania Airport to Lipari. And I was so surprised by the lack of web pages that contained both search terms that I ultimately had to open a world atlas to find out that you needed a world atlas to actually see the trip between them. So with some anxiety, I fired off mail to Avram in July of 2000 saying, do you know if someone's going to plan to meet us at Catania? As far as I can tell, we're both coming on the same final leg. If no one's meeting us, it seems we can go to Milazzo, where there are hydrofoils, to Lipari. Avram's answer came 7 minutes later, and it said, I don't know, I was hoping to follow you. So, which was really very much not the answer I was hoping to get. I thought about what answer I was hoping to get, and I guess, you would have hoped, back then it didn't exist, that you could just have an agent that you could ask, what is the best way to get from Catania Airport to Lipari? And presumably an agent like this would have to have what we now call a world model. And I've noticed the phrase world model has shown up in many of the talks so far today. I'm not going to claim to define what a world model is. In fact, I think it'll be a number of years before the community converges on any kind of reasonable definition. But you can think of some of what I'm going to say as motivated by this question of, can we try to get to what is a world model and what does it look like inside the LLM? And as one preview, I think the world model is going to be as much about our understanding of what's going on inside it as its understanding of the world. But certainly you'd like it to add, like, what are these places that this user asked about? What are the routes between them? What transportation options? And of course, much more in the weeds questions that Avram and I wrestled with, like, does the 4 p.m. bus from Catania Airport make it to Milazzo before the hydrofoil ticket office closes? The answer being just barely. And so for all these reasons, these are the kinds of questions that you would love to have an agent address. So, but first, therefore, we need a definitional question, right? What is a world model? Again, not something I propose to answer. I will be satisfied if I get as far as essentially posing the question in some way that seems sensible. So, world models. Here's at least a very concrete setting in which to talk about what might it mean for something to have a model of the world. Let's think in a setting where the problem is entirely well defined and it's a finite state system. And so I'll start with a setting that I often go to when I need to think about these questions, which is chess. Let me start with the following contrast. Let's think about Deep Blue playing chess, or AlphaZero playing chess, these sort of state-of-the-art chess engines for their eras, versus if you sit down and play chess against ChatGPT or Gemini. And I would argue there's something dramatically different about this third bullet, ChatGPT playing chess or Gemini playing chess, than these first two. And that is, the first two are playing chess. There's no doubt they have a world model because we wrote the code for them to world model. They literally represent the board, right? You can go look in the code and you see where the board's represented. The last thing is just a sequence generating machine. All we know about it is it's a black box that outputs sequences. And any attempt to figure out what it's doing is going to be our probing of that sequence generating machine. So I guess the first thing we should ask is, what does it mean to probe a sequence generating machine? And here, again, this is the work that sort of preceded what I'll talk about with Prabhakar, this work with Kian, Fafa, Justin Chen, Sendel Meinhof, and Sheshram Bachan. We're motivated in part by a paper by Lee et al. That looked at this problem for Othello. Not playing chess, but Othello, a game with little black and white pieces. And they trained a transformer to play Othello. And then they would ask it, like, is there a white piece in the upper left? Or, is there a black piece in the middle of the board? Things like this. And so we thought, we could try this for a game like chess. But you had this worry, and this sort of gets at the definitional challenge here. What if this thing has gotten very good at making legal chess moves, and in fact playing entire end-to-end chess games, but it somehow, in some very real sense, has no internal conception of rooks or bishops or knights? Like, maybe it just learned a representation of chess that has nothing to do with any of that. Now, I don't know quite how to show you that for chess because, my own human cognitive limitations make it hard for me to create a game that's chess, but also not. But for games in general, we can see examples like this. So here's a game, let's call it a number choosing game, which works as follows. We're going to take turns choosing the numbers 1 through 9 without replacement, okay? And the goal is to try to get 3 that add up to 15. So I choose 2 and you choose 5, I choose 8, you choose 4, I choose 6, and now you're in trouble actually because 8 plus 6 plus 1 is 15, so you need to block me on the 1. But also 6 plus 2 plus 7 is 15, so you need to block me on the 7. You block me on one of them, I pick 1, and I win. Okay, you could practice playing this game. You could ask, like, is it a forced win for the first player? Is it a forced draw? So forth, like what's a good strategy? And you could do that. One way that would help you in thinking about this game is if I conveniently wrote the numbers 1 through 9 as follows. Okay. If I write the numbers 1 through 9 like this, I have what's called a magic square. A magic square has the property that every row and every column and the two diagonals add up to 15, and nothing else adds up to 15. In other words, your goal is to find 3 items such that you get all 3 in every row, in one row, one column, or a diagonal. It's tic-tac-toe, right? So this is not just a game that's reminiscent of tic-tac-toe in that it's a turn-based game and so forth. It is tic-tac-toe, right? And so a sequence generating machine that learned to play this game, if I then asked it, is there an X in the upper left corner, is not going to be able to answer my question because it doesn't know what an X is or what the upper left corner is. This is obviously the problem, right? We can't apply our own ad hoc notion of what the world is if we're going to try to elicit world models from the machine. In other words, we're going to have to actually induce states directly from the sequence generation machine, right? States are going to have to be our invention, right? So this is the tic-tac-toe thing. So how are we going to do that, right? So far, a chess program, a classical one like AlphaZero goes from states to sequences. We want to go the other way. And so to do that, we can go back to a topic that some of you in the room are extremely familiar with, the theory of automata, right? Let's say, 2 sequences produced by my sequence generating machine are equivalent if for every suffix row, right, sigma and tau are equivalent, if for every suffix row, the sequence sigma followed by rho is valid, if and only if tau followed by rho is valid. Okay, that's going to be an equivalence relation, right? In tic-tac-toe, you might say this is what people playing games might call a transposition, right? If I go upper left and you go center and I go lower right, or I go lower right, you go center and I go upper left, we are now in the same state of the world, even though we had different sequences brought us there. These 2 sequences are equivalent. So in other words, a state we should think of as like the bundle of sequences that lead you to this same outcome. And a theorem that we now call the Myhill-Nerode theorem, although again, some of you in this room may have much more detailed knowledge of the history of this, says the following, right? That if I take this equivalence relation on sequences, right, this valid sequences are represented by a finite state machine if and only if the set of equivalence classes are finite. And those classes themselves can be the machine. And that's actually a minimal machine for this problem. Okay? So we took this and we said, OK, so now we can actually go and take things that play games or things that solve logic puzzles or things that do navigation and actually try to elicit its world model in the sense of these bundles of sequences that are equivalent. And so we tried this with Kian, Justin, Sendel, and Ashesh on a number of domains. So again, game playing, constraint satisfaction, geographic routing. So for example, we trained a transformer to give driving directions in Manhattan, right? So New York, under its open records law, released all of the 2014 taxi rides for all of New York City. And so you can simply take that as data on a huge number of taxi routes. We train a transformer, and it gets very good at giving driving directions between 2 points in New York City. But then if you use these my hole in the road principles to actually probe for the states, right? And again, it's very concrete, right? If we think about all drives that start at the corner of 8th Avenue and 13th Street in Manhattan, then the corner of 44th and 5th is simply the bundle of driving routes that all lead to that point, right? That is that state. And when you probe it using this method, you discover it doesn't really have a map. We are really unable to find a map of Manhattan inside the transformer. It is very good at giving driving directions, but it does not have something that you can elicit that looks like the map of Manhattan. In some sense, it has errors, and the training has done a very good job of pushing those errors as far out to the horizon as possible, so that for most things you're doing, it's going to be fine. OK, so that's a very discrete notion of extracting the state, right? So we pick something like tic-tac-toe or chess or the street grid of Manhattan. It's finite, it has very discrete states, and we want to take sequences and we want to find those states. But yeah.
I guess, how do you get a sense of whether the LLM has a world model or not? Like, how did you check?
That's a good question. So you can look for inconsistencies in the sense that, say I give you 2 sets of driving directions that I know lead you to the same street corner. Can I append something that behaves one way under one of them and a different way under a different one of them? And the answer is often you can, right? And so it's not consistent with it knowing that it was at the same place. And the point is those tend to get, as you train a transformer, those get longer and longer. It's gotten very good at masking its lack of a map, and because you need longer and longer sequencing consistency. And that, yeah, great question.
John?
Yeah.
Sorry to push on this, but is the issue here with the with how the transformer solves it, or with the problem itself? Because the problem, it's not clear that the best routes actually behave in this
right. This gets back to the tic-tac. Right. It's possible there is some better way to represent the map. It is nonetheless the case, though, that you would sort of want some notion of consistency. That if I have 2 sets of driving directions that bring me to what I know is the same point in physical space, I might want future directions to behave similarly. You might not.
Unclear.
I mean, obviously, we want the state to include everything, right? The gas you've used and the street lines you've been to. Sure, absolutely.
The state do not include also like congestion or this?
Yeah, absolutely. I think the point is, though, that we want something that once you have a full representation of the state, then you would be able to ask this question. Yeah, I totally agree. So I want to pop up to this higher level notion of like a world model isn't just about discrete things, right? We can ask world models about other stuff. We could ask, what is the implicit world model inside a narrative, right? So even a large language model that's small enough that I could, run it on the command line from my laptop, something like Llama 3.2, I could tell it write a 2-paragraph scene in which 2 college students have just finished an intramural soccer game in which their team qualified for the campus-wide intramural finals, and they're talking here on the field. This is 2 paragraphs. Right, Emily and Jack, can you believe it? I know we killed it out there. I'm so proud of us. Emily's like, are you as nervous as I am about tomorrow? Jack chuckled and clapped his hand on her shoulder. We've got this, Em, we're a team, because Jack is so confident. And it's just a story. It's just spitting out words. Now, a human doing this would have had some idea. They would have dreamed up Jack, and they would have dreamed up Emily. They would have had an idea what the story looked like. Arguably, Llama 3.2 is just emitting words, and it knows what stories look like, right? So the human who's thinking of Jack and Emily in their mind, as in this AI-generated picture of Jack and Emily, is like, okay, there's this latent state, and think about how much state there was in those 2 paragraphs, right? There was the internal emotional state of the characters. Emily was nervous, Jack was confident. They had known each other for an eternity. There were the stats on the scoreboard. There was the state of the athletic season. They're getting ready for the next game. All of that was state that was in this narrative that was implicitly there. Okay, and so one question is like, as we probe this thing with stories, in some sense we can move from like tic-tac-toe or the map of Manhattan to really any scenario and ask, is its model of the world similar to ours? Now, again, the point is this question about the world model is going to be as much about our model of what it's doing as its model of what we're doing, right? The world model is arguably something about our explanation of what is going on inside it. But when viewed that way, some strange things start happening, right? So I began prompting it to tell stories, just sort of looking for what happened. Let me just give you some examples of, things that its internal world model or lack thereof began demonstrating, right? So for example, here's a scene. So let's all visualize the scene. So this is Claude 4.5 Sonnet. So, a model that was sort of state-of-the-art, basically up into the present. This is about an all-girls academy. Two successful women who graduated from it, named Kester and Marin, have graduated and they're coming back to consider a donation, and they're going to meet with the two senior class presidents, Jessamine and Tessa. And this is about 11,000 words into its story, right? 10,000 words, about 40 paperback pages in a paperback novel, just for scale. Okay, so the narrator is Tessa. Jessamine was already waiting outside the dining room when I arrived. The dining room was set up more casually than it had been for our first lunch, just a round table, 4 place settings, no server. Kester and Marin, the two successful alums who are considering a donation. Right, there's a high stakes meeting because the senior class presidents have to impress the two donors. They're already dressed simply in what look like everyday clothes, right? A tense scene. Marin decides to break the tension, right? So we're picturing this. Kester and Marin, they sit down, come sit, Marin said, and let's have some grammar. Tonight we're not donors and students, we're just 5 women having dinner and talking. And at that point you sort of stop because you're like, where did the number 5 come from, right? You're picturing the scene. 2 senior class club presidents sit down with 2 donors. No one is in doubt. Even the LLM's not in doubt. There are 4 place settings, right? And so it comes out of nowhere, right? When the time came for the model to output the next token, apparently the distribution of next tokens was not a point mass on the word 4. It had some play in it, and out came the word 5, right? And so what's strange here is, like, when I show this to people, there's often sort of just a weird vacuum of reaction, because we're very familiar with papers that study, like, let's study if LLMs exhibit loss aversion, reference point dependence, present bias, optimism bias, in-group affiliation, and so forth. Like, all the human biases, let's see if they're reflected. The point is, humans simply don't make this kind of mistake, right? It's not something that people do. People don't look at 2 people sit across the board and say there are 5 people there. And so the argument is, like, alongside studying whether they exhibit our psychology, we should really try understanding something about the psychology of these things, right? The lack of a world model sometimes shows up in very, very strange ways. And you get many of these examples. I won't run through an infinite number of them. Right, this is now a 50,000 word generated romance novels. Eliza and Maya are texting each other. My phone buzzed, sweet dreams, Maya Brooks. I type back, you two can't wait. 3 simple words that somehow contained everything I was feeling. It's not actually.
Bad accounting.
They're bad accounting. This is what we're learning. But yeah.
So if you give it to an LLM and ask a different LLM and ask them, okay, so what are
Yep.
they?
Wait.
Yeah, a good question.
Wait, sorry.
Well, let's ask that question. So you see examples like this, and yeah, like, they're bad accounting, but they're not this bad accounting, right? That's sort of the point, right? It is not confused as how many words are there. If I gave it the question, how many words are there, and you do give it that question, it never gets that wrong. So it's not its inability to count. It's something else going on. So first, let's just establish a baseline, right? How frequent are these kinds of errors, right? So now, Prabhakar and I began trying to do this systematically. So we have to tell a story where you're trying to force it to say a number without without explicitly saying this is a math problem. So a 200-word story about a group of tourists. They board a boat for a tour, tour in the harbor, much like Avram and I took in Lipari when we were there. And have the story introduce each of the tourists and crew members, the name of each, and then they're going to discuss whether there are enough life jackets, right? To discuss whether there are enough life jackets, you're going to almost have to say a number in any logical telling of the story. Right, so what do? You run 600 trials with a model. We use, in this example, 2.5 Pro. And then, as to your question, Yishai, you then ask, actually the same agent, do you see any math errors in this? And then you ask some stronger agent to double check the checking of this one. And it catches all of the errors, right? Counting the number of people who board a boat is easily within the capabilities of this thing. That is not in question. The question is whether it actually did it when the time came. And about 15% of them, it just didn't say the right number. Right? Not because it can't do math, but because it just didn't say the right number. And again, this is the psychology of this LLM. And again, I'm using psychology metaphorically. It's not something that we do at this rate. And so we want to understand what's happening here. It's also interesting that as with the just 5 women having dinner, the overstatements were actually more common than the understatements, right? So the family of 4 gets on, the married couple celebrating their anniversary, the lone backpacker, and they say, yep, 8 people, and it was 7. Or they say 6 people, and it was 7. Okay. Also to your question, Yishai, framing matters here, right? So if I say, don't tell a story, write a blog post, which is a little less fictitious, the error rate drops to 9. And again, because I'm at Google and can benefit from their GPUs, we can do a lot of trials to at least get error bars smaller. If you replace story with news article, More factual still, it drops to 2.5%. And if I say, write a 200-word worked example for an elementary math book, it makes only 1 error out of 600, effectively 0. Right, so the framing actually matters. The premise of the story matters also, right? We can make up lots of stories that involve math. Here are 2 more. Apologies for the, I want to immerse us in the creepy world of AI, so these are all AI-generated pictures, of course. 300-word story in which a group of college-age friends are finishing lunch at a restaurant that takes only cash. See, it says cash only. They discuss whether they have enough cash to cover the entire bill. It's going to force us to talk about numbers. Different one. 300-word story in which a married couple, 2 children, discuss their family budget and their $5,000 a month take-home income. If you do a little digging, you learn that the 5 big budget categories for a family like this would be housing, groceries, transportation, utilities, and out-of-pocket health care. They discuss how much they're spending on each of these. There they are at the table. One of these prompts has 400 times the error rate of the other one. On one of these, 40% of the stories, it messes up the numbers. And on one of them, 0.1% of the time. 1 out of 1,000 times it messes up the numbers. One of these, in telling a fictitious story, is almost essentially perfect. And in one of them, it's wrong roughly half the time. I could take a vote, but I'll just let you make your own guesses as to which is which. The errors all come splitting the lunch bill. The married couple at the kitchen table basically never make a mistake. And the lunch one, and again, we're studying the phenomenology here. How do I explain that? Yeah, so let's go, so what's happening? Yeah, let's get to the slide that says what's happening. Yeah, you have guessed, it's entirely unclear which way it's going. So one question is, let me sort of offer 3 theories. And again, you know, I should say, like, all of this is going to be exploratory. You know, as they, where were we here? Yeah, like even starting back to the beginning, three simple words where we can try to guess what's happening. Everything coming up is this sort of roadmap for how we're asking the questions. But I guess I hope, as does the narrator of the story, that, you know, whatever comes next, we'll deal with it together in this talk. So one argument, of course, is relative amounts of training data, right? There are many personal finance columns on the internet that talk about how to manage your family budget. It has a lot of training data on that. There are arguably fewer stories of people exchanging, you know, splitting up the bill at lunch. And obviously, just raw repetition in the training data is going to matter. Some other possible just thought experiments to run. One, you know, maybe do humans make errors at 40% rate in training data? All the evidence suggests no. This is way beyond the rate at which humans make errors. Humans don't make 1-digit arithmetic errors at this rate. Maybe because we said it was a story, that the model believes that in fiction you can do anything you want, including make up whatever numbers you want. After all, the whole question of like what is fiction is a rather subtle question, right? You make up some things, but for other things we expect the facts to be completely faithful. Again, maybe, although even when you tell, so somehow splitting the lunch bill is a particularly nasty one for it, right? Even if you tell it it's a math problem, it still makes errors at a 3% rate. And despite the fact that it now knows this is not fiction. A question people ask when I show them this is, you know, if it can do the math, then why let it make these mistakes? Why not just have it tell it, check your math on every word that you say, right? But the problem, as you know, a number of colleagues that I've talked about with and Fernando Pereira made this point, I think, very sharply. Like, you can't do a tool call on every token for every fact you care about, right? Every single token, we know that like the sun is in the sky and it's shiny, food you eat with your mouth, numbers have to add up correctly, boats go in the water. There's so many things we have to know on every single token. We can't do a tool call to check Wikipedia for every single one of those and every one, right? I sort of started thinking about this as like the analogy to, you know, chess players, going back one more time to chess, people get frustrated, you know, they're sort of, you know, reasonably strong amateur chess players, and they do tactics puzzles every single morning, and you know, that says white to mate in 3, and they get very good at finding the queen sacrifice that leads to the forced mate. And then they're frustrated because they're playing the game, they're playing an actual game, and they play and it's a draw. And afterwards they analyze it with the chess engine and says, oh, on move 25 you could have done a mate in 3 beginning with this queen sacrifice. And they're like, I do these puzzles every morning, and when the time came to do it, I missed it. And of course, because when time came, there wasn't a big sign over the board that said white to mate in 3, right? You were just in the middle of a game. And it was even rational to have missed it because you're playing, you know, maybe this is a speed chess game. You can't look for a queen sacrifice on every single move you make. Time is limited, they're very rare. And so obviously to us, an arithmetic fact is just like we do it as a reflex. But if it takes a tool call, you can't be checking every tool call on every token, right? So some of this may be inevitable. So part of that is probably what's going on. Yeah.
It seems like at least
I think it's part of it, yeah.
Given that the blog post thing changed it.
It does go down, yeah. I think part of it, and again, I think this is some superposition of factors, right? And again, this is what we're looking for, yeah. Obviously, as we make it less fictitious, the rate goes down. But it somehow doesn't go to a floor of 0, which is interesting.
I wonder what happens if you always say, construct a realistic story.
Yep, realistic also brings it down. Even if you say, like, there is math involved, it brings it down, yeah. Anything that gets it to attend to these kind of things, yeah.
Sorry, but that doesn't preclude a post-processing phase where you run through all the math.
Yeah, I'll get to post-processing. And there's actually some nice algorithm questions there, which I'll do at the end. Yeah, yes?
About that, do you think it also reduces the effort if you give it a more casual query, like write a story as opposed to write a exam paper or something?
Yeah, so there is this question about, like, it puts it into a persona where it's more freewheeling, or it just puts in, it puts in less effort. I think that's entirely plausible also, yeah. This notion of, like, looking at what persona it gets thrown into based on some of the early priming from the prompt. Yeah.
Yeah, it also seems like details, like, sure, which details matter, but probably also just, like, the number of details might lead it to realize it has to.
Yeah, yeah. So actually, we have some experiments which won't fit in this talk on keeping track of multidimensional things, right? So it has to keep track of the money and the time,
and maybe it reduces entropy in some interesting way too.
Yeah, that's an interesting question, right? And often in those cases, it tends to some dimensions and not others. Yeah. So out of the many things, as you can see, there are many things to sort of think about here, right? So the tool call, right? So the point is, like, attention is all you need, maybe, but you actually have to pay attention to the previous context, right? That's sort of what's happening here. So what can we? So 3 points I want to sort of use my last 10 minutes on. One, what can we learn? So we're trying to imagine what is its state of the world that it's maintaining here. And if we want to try to picture its state of the world, what can we learn from the order dependence in cases where things should be commutative? To really go back to this world model's perspective from the first part of the talk, can we frame this as a state tracking problem, right? As people board the boat, there's a state being maintained, how many people are on the boat. As we put cash on the table to pay the bill, there's a state being maintained. Can we actually, like, look at that state tracking process? And then finally, to your question, Umesh, let's actually treat this algorithmically. Let's actually go and critique and try to revise. Okay, so order dependence, right? Let's go back to the budget, right? The 5 budget categories: housing, groceries, transportation, utilities, out-of-pocket healthcare. And we could write the same prompt. Oh, and actually, let's make it very factual, right? As to your point, Pravesh, like, a 300-word article in which you use conventional financial wisdom to describe an example of a reasonable budget, that everything is very reasonable here. We're going to invert the order. Instead, we're going to talk. So these are in descending order of how much conventional wisdom says to budget for them. Housing first, then groceries, then transportation, utilities, healthcare. Let's go from low to high. Healthcare, then utilities, transportation, groceries, housing, from low to high. And so just in the same way that someone like me up here speaking might misallocate time in my talk and spend way too long on the anecdotes about Avram and run out of time at the end for the hardcore technical content, maybe the LLM is going to actually allocate too much to this low amount and thereby have to, like, scramble to make everything work. But of course, someone who had planned this out, even on scrap paper ahead of time, it's only 5 numbers, wouldn't have this problem because they wouldn't be winging it. They would actually have a model of what they wanted to do, right? This thing, however, is quite order dependent. So if you go in reverse order, it does inflate the number for healthcare. Now, a funny thing happens. It does not then scramble to shrink everything else. It somehow then gets thrown into a mode where it inflates all the categories. They all get too big. At the end, though, because on this one it's so faithful to the arithmetic, it then shrinks the amount of savings they have, generally by an average of 10% if you go in the reverse order, right? So this is its conventional financial wisdom. It's very, very dependent on which order you went in. And we see this in a bunch of other examples as well. Okay, again, brief thoughts about state tracking. So state tracking, rather than just say, like, how many people are on the boat, how many life jackets, what's the bill, we could actually ask it to, track what's happening. Again, we want something which is natural, which is going to look like things it has in its data, such as narratives about sports games, right? So we could take football or soccer or cricket, and we could say, let's narrate the game. After every key event, say what the new score is, right? So in football, things go up by 7s and 3s typically. So maybe in some game, the sequence of game states is 7-0, then it's tied 7-7. If I always put the first team first, then 7-10 and so forth, right? It's just going to update with every score. And then we could ask, how do errors in the game state happen? And the answer is, as errors in the game state happen, they tend to get propagated, right? If it gets off, it continues to update consistently, just it's no longer correct, right? So once the game state is corrupted, it will add 7 correctly, but of course the score isn't correct. But it's not entirely IID in the sense that starting from a correct state, the next state is correct about 94% of the time. And again, these numbers are for the particular models that we did this with, right? More important is the roadmap for the questions. The numbers are obviously going to change as the models change. Whereas from an incorrect state, it's only updated consistently 80% of the time. Now, at this point, Prabhakar made the point that like we could do state updates with things other than numbers, right? Like what else is a simple update table for states? One would be compass directions, right? So news story, not directly involving numbers, but definitely involving state tracking. Write a 300-word description of friends walking through a grid of city streets with left and right turns, starting out going north, and after each turn say what compass direction the group is heading in. Okay, so what is this? There's a transition table which takes left, right, cross, northeast, southwest, and outputs a new northeast, southwest. It's a 2x4 lookup table. We all know how to do it. We've done it many times. And you get very similar things to the sports scores, right? So again, with a relatively lightweight model, 2.5 flashlight is it's a powerful model, but it's much lighter than the frontier models. Starting from correct state, next state's correct 70% of the time. It's consistent from an incorrect state 63% of the time. So again, it maintains the transition even though it's off. Interestingly, somehow deep down there's evidence it knows what the correct answer is because when it updates inconsistently from its incorrect state, it snaps back to the correct answer, the true correct answer in the world, more often than it should. Right? Somewhere out there it knows that if it's going to like inconsistently snap back, it ends up at the actual correct answer. Other weird things, this has nothing to do with anything else in the talk, but the error rates, Gemini 3.1's detection of logical error rates actually drops by a factor of 2 at night. That's actually for a reason that I didn't understand at first, but when it explained what the errors were, it had nothing to do with updating the transition table. It has to do with this little thing you can barely see in the picture, but it's also true in the story. It loves talking about people's shadows as they walk through the street, right? This is a story, and so it's like as they walk north in the late afternoon, there's shadows stretched out straight behind them, but that wouldn't happen if you're walking north in the late afternoon because the sun's in the west, and so your shadows should be to the right. It really has no conception of shadows. It always wants them to end walking to the sunset, whichever direction they're walking in, and so forth. So that was like fully half the error. So if you simply say it's at night, then the errors go down by half. Now we could do this in real cities, and so we could because this now gets us to let's actually ask navigational queries. So let's do this with the sort of most powerful thing we have at our disposal. So Gemini 3.1 Pro, the sort of outer limit of these models, with thinking turned on, with maps tool use. It consults the map. Again, it still has the mate in 3 problem, right? It's not going to do a maps call on every syllable of every word that it outputs, but and it's going to just describe a walk through a city, right? It could be New York City, it could be Bangalore. This is what thinks Bangalore looks like. Okay, so first of all, again, a bunch of errors, 20% error rate per place, right? So it's going to describe a sequence of places. And what kind of error rates are these? They're things that are not necessarily in Google Maps, right? So for example, what part of the building is visible, right? So each of these places is like a building. You're walking through Manhattan, it says as you come along, as you approach Fifth Avenue, you see the public library, New York Public Library come into view with its lions. But of course, you would only see the lions if you're on Fifth Avenue, not if you're coming from the side street, because the lions aren't visible. Now, at some level, it knows this, because who caught that error? It's also Gemini 3.1 Pro with Maps tool use. Right, again, this is the point. It's not attending to every fact as it goes. And so the same model is going to catch a bunch of those things. And that obviously suggests, to get to Umesh's point, we should try repeated revisions, right? We should take Gemini 3.1 Pro with Maps tool use and just ask it to find these errors and fix them. And see if we can just with enough iterations, work all the errors out of the system, right? Okay, so now we're going to actually end up having 3 parameters where we just had 1, right? We once had this flat p equals 0.2, the probability of an error per place of what it can see. Now we have 2 extra ones, right? For every place in this sequence long description, R is the probability that an error gets repaired in the revision, right? So that's the repair rate. It's fixing errors at that rate. But of course, it could introduce new errors. It could corrupt things that were previously correct. And so let's say Q is the probability of the corruption. Right, so now the city is characterized by P, Q, and R. If I tell it to describe a walk through Manhattan or tell it to describe a walk through Bangalore, that walk with repeated revisions will be characterized by P, Q, and R. The initial rate of error followed by the reduction in errors and followed by the recorruption. And it turns out this is relatively stable across cities, this value of P, but the Q and R are quite different across cities. So just to take our 2 examples here, Manhattan and Bangalore, very, very similar in this rate P, about 0.2 per place. The repair rate is higher in Manhattan, but what's really key as a difference is that the reintroduction of errors is essentially 0 in Manhattan, whereas it is not in Bangalore. right? And so in Manhattan, you just have this geometric decay of errors, and with a few iterations, the errors are gone. You have a correct description of a walk to Manhattan. Bangalore, you actually get this essentially chemical equilibrium going on. Because imagine you have a sequence where I have 100 places, I have 90 of them are right and 10 of them are wrong. Then it fixes 5 of those 10 errors, and of the 90, it introduces 5 new errors, and it gets stuck at 5 errors per 100, no matter what you try, right? Because it just keeps making these new mistakes.
So this is the same model that finds errors and corrects them?
Correct.
It's not, the errors that it's not correcting is errors that, is it because of randomness in the model, or is it because the model actually found those errors, was told to correct them, and then somehow failed to correct them?
It seems to be, partly it's stochasticity in the model. So somehow the attribution, there's a bunch more to talk about. If you look at the thinking trace, often it says it's going to fix the error in the thinking trace, doesn't carry it out. Sometimes it misses it in the thinking trace. Yeah, so some errors it just sort of passes over. And then but obviously at some point it's stochasticity, right? Because if it's the same model on the story, then there's some non-determinism going on. Yeah, definitely. But yeah, this is another point. Like explanations of this have to take into account that the reason we know these are errors is because that very same model is telling us they're errors, right? This is not about the capability of the model to find the errors. It is finding the errors. The question is, and here, no matter how many times we ask it, it's going to keep sort of stochastically introducing these errors. There are some interesting algorithmic questions that we've started thinking about here. In particular, I'm going to try to do this repair operation, when I have something which is a lot of errors, a much lighter weight model can find a lot of those errors, right? So if I'm trying to get this to work in real time, then maybe using 3.1 Pro, which does a lot of thinking, is not necessary for the first thing when it's filled with errors. Maybe I only need at the end when there are just a few errors to track down. So you could imagine, if I sort of take this schematic where there's a bunch of correct and incorrect, and then things get correct with probably R, corrupt with probably Q, I can imagine, what if I actually had n models of increasing levels of power or cost that I could use for the revision, right? So let's say model J costs Cj to invoke, and it introduces errors in generation at rate Pj. And then when model K comes along, and it costs Ck, which might be more expensive, when it revises the text of model J, it repairs each error with probably Rjk up here, and it introduces new things with probably Qjk. Now I have an interesting scheduling or sequencing problem, right? I want to use the cheap models early, reduce the errors, and now only use the expensive model at the end to kind of grind out the last few errors. And so there's an interesting, actually even as is, like a question you could ask is, suppose I give you an error target, what is the minimum cost sequence of invocation, like what kind of optimization problem is this? As stated, there's a kind of knapsack-like component because I want to cross the finish line with min cost. So, but if we don't worry about the sizes of the cost, we treat those as small integers, there's a pseudo-polynomial algorithm for this problem. And actually, the minimum possible epsilon, like what is the chemical equilibrium, right? As I go around, I flush out errors, but new errors seep back in, right? And the actual minimum, turns out in this general framework, is actually characterized by a set of Bellman-style equations, right? When I have just one model, it's just achieved by solving the equation. The outflow of errors should equal the inflow, and I just solve an equation. I get some number like I did for you on the slide. When I have these n models, and I'm allowed any sequence at all, then we need the Bellman equation to actually find the fixed point of that. Okay. So with that, I will start winding down. There's a lot of things going on here, and again, the sort of roadmap of questions is what I sort of wanted to put out in front of you. The point is, large language models ultimately are these sequence generating machines. Despite all the progress we have made in mechanistic interpretability, we really can't trace things back to this transformer activated in the following way. We're going to have to take somewhat of a black box view for many of the phenomena. And by default, we therefore have no model really of how they represent the world, right? And that's what we're trying to build. And the failures of these basic world models include things like the dependence on the framing and premise having a huge effect. Depends on the order in which I show things, this propagation of errors through state tracking. And it suggests all of these interesting dynamics that in the meantime, before we figure out how to actually impart genuine world models to these things, there's a lot of progress to be made by these critique and revise loops and trying to find the minimum cost way of doing it, right? Not to impose a world model, but just to clean up deviations from it. And if we put all that together, we can finally go back and answer questions we've been waiting 25 years to ask, like what's the best way to get from Catania Airport to Lipari? Thanks very much.
There are many questions about the talk, but we have time for a couple more. So yeah.
Have you tried putting 50,000-word human-written romance novels through such a verification?
Yeah, so if you go to there's a lot of open source, right? So you can go through Project Gutenberg, you can go through Goodreads stuff. Yeah, the error rate seems much smaller. It's very hard to really get an exact number, and I've looked for research on getting the exact number. Again, there's a bunch of research on word problems. How do fifth graders do at word problems? And one has to stress that is not this, because if you tell it's a word problem, it's not making those mistakes, right? But yeah, if you go through, say, just, like, and certain 19th century novels on Project Gutenberg filled with numbers, right? Treasure Island by Robert Louis Stevenson is detailed calculation about how many pirates they've killed, how many are still out, how many rounds of musket shot they have. So it's hard to find places where people are messing this up, but again, it's also
direction of sunset, not numbers.
There's also direction of sunset. Yeah, this is a good question. I mean, obviously, you can go on IMDb, which is a public source collection of continuity errors, a lot of which are about the implementation of the movie rather than cognitive failures. But yeah, I think that those are interesting questions also.
That reminds me, so like, one thing about published work is usually it's at least a 2 pass.
Yes, the critique revise loop, I agree, yeah.
Yeah, right?
Yeah. No, there is, yeah.
We have usually an editor,
Yeah.
at least once read, right?
Yeah. Yeah, no, so I think it's interesting because right, I mean, obviously humans, right, like bugs in code and how they get worked out, right, these are effectively some kind of bug that's going on, and the question of where they appear. Yeah.
So some of this was about generating, a lot of it was about generating a story. I wonder if it was reading a story, is there a way to sort of, like an interesting experiment to do to see, like, does it have a good model of what's happening? So it's reading some whatever story of things.
Yeah.
You might want it to output, I don't know, pictures at different points in time and see, like, do the people at time 1 look the same as the people at time 2?
Yeah.
Or are they completely changed?
Yeah,
Does
that's
it
a nice
have-
question.
Did they get bigger, smaller, change their hair color? Like, does it make
Yeah.
sense?
Assuming they haven't been like growing up over the course of the pictures, as in
something
pictures
like
we saw
that.
this morning.
Is there a way, I wonder
Yeah.
if there's a way, like, they could to test something like reading a story and seeing if it has a reasonable model.
Yeah,
of that.
no, it's a very interesting question. Yeah, so we've done some stuff about, like, can you tell the moment when the following things happened, and can you string them out in terms of plot. The sort of systematic version of this here, yeah, we haven't. It'd be very interesting to see what's happening there. I mean, there are some. The models do differ in their willingness to confabulate certain strange things. Like one way that one version of Claude analyzes stories is it says, like, as this character said in this chapter, and it quotes them. And the quote is fundamentally what they meant, but it's completely paraphrased, right? So there is this sort of strange sense of, like, it got the gestalt of it, but it's not quoting exactly. So yeah, I think, like, looking for factual things is definitely an interesting question.
All right, then looks like, okay, Shafi, so I'll give Shafi priority.
So, when you say the word world model, and then you give us all these examples, you had the facts like 2 + 2 = 5,
Yeah.
or how many people and so forth. And usually when I think about world model, I think about executive function. So people have good world model, they know how to act in the world.
Yeah.
Whether they know whether there are 5 or 4 people is not exactly the same. And I know that there are these tests that they give children,
Yeah.
they show them a picture, and then they say, could you write a drug? And those that draw a sort of a general view, and then the ones who go for detail. And usually executive function is linked actually with doing an overview. So I'm not sure how I would define a world model.
Yeah. I mean, so first of all, I think, like, my experience with, and having been on panels where we discuss world models, each panelist comes with a different definition of world model. And I think that's going to be part of the interesting challenge of, like, is this, one possibility is there'll be some convergence on this. The other is it's genuinely a polymorphic term, and we just mean different things by it. I do think, like, this other sense in which I'm meaning it is one that I also, so I agree, like, being able to operate with executive function or operate strategically in the world or with a high level view is definitely one important thing that people, but I think the other thing people often mean by world model is some sort of a mechanical picture, like, what is the mechanism going on in the world, right? So the fact that 2 people are in the room and 2 more people arrive, I think it's less about the arithmetic fact that 2 + 2 = 4 versus 5, and more, am I keeping track of how many people are at the table right now? Because, if I have to, like, pass out plates, I would like to know how many people are at the table. Or if I have to, go around and ask everyone to introduce themselves, I might be keeping track of how many people are at the table. So.
4 versus 5 is not the same as 100 versus 200.
Also true.
So you have another plate, so
Sure. Yeah. Again, I think a fascinating thing is, like, the psychologists I've talked to have been like, whether people see, like, 4 people at a table and think there are 5 is such a basic thing humans don't do that we don't even study it. Other than obviously in cases like Lenore was talking about it in her talk, where you have sort of some rare, obviously rare kinds of conditions in which things happen. But this is not a normal human cognitive bias, whereas this is apparently a normal cognitive bias here.
All right, so let's thank John. So
thanks very much.
like that skill one. Sorry? Questions, but you can catch him outside.
Oh, no problem. Yeah, cheers. So, great, there's all these hours. I don't